Again, the big takeaway for today is after deciding what types of intermolecular forces any given molecule has, you need to recognize that the intermolecular forces reflect how strongly molecules are attracted to each other inside a sample, which is another way of saying that intermolecular forces dictate how molecules interact with one another. And so on a fundamental level, one of the biggest things that intermolecular forces and the strength of intermolecular forces dictate are the physical properties of pure chemical compounds, like how high their melting points and boiling points are. So in general, if you know the types of intermolecular forces that a molecule possesses and how big a molecule it is, such as what its molar mass is, you can make quick and easy comparisons between a series of molecules and decide which of them will have, say, the highest boiling point and which of them will have the weakest boiling point, the lowest boiling point. The stronger the intermolecular forces and the higher the molar mass, the higher the melting and boiling point of the compound is going to be. In general, intermolecular forces count for more, but if the intermolecular forces of two molecules are similar, the heavier molecule will have higher melting and boiling points. Another way of looking at that is to say that if you were to compare simple chemical compounds, simple covalent compounds, and make their central atom an element in one of the left-hand non-metal groups on the periodic table. So make a series of molecules where the central element is a group 14 element. And you do that for every element in group 14. So for instance, you make CH4, methane. You make SiH4, silicon tetrahydride. You make germanium, GeH4. You make a tin hydride, SnH4. You've made a series of similar molecules which should have similar intermolecular forces. And all that's happening is they're getting heavier as you go on. Lower molar mass, higher molar mass, higher molar mass still, higher molar mass still, because each of these central atoms, carbon, silicon, germanium, and tin, live in the same group on the periodic table. Tin is the heaviest. And you could do an experiment. So for instance, you would see what is the boiling point of each of these compounds, and you record their boiling point. You see the temperature at which they transition from a liquid to a gas. What you would find is that for a series of molecules like this, the lightest molecule will have the lowest boiling point. Methane has the lowest boiling point. The heaviest molecule, highest molar mass, has the highest boiling point. Tin hydride would have the highest boiling point. And then, having discovered something, that the boiling points of these compounds increase with molecular weight, you might try the same thing with the other three non-metal groups on the periodic table. Try it for group 15, which is nitrogen's group. Try it for group 16, which is water's group. Try it for group 17, the halogens. Do the same type of experiment and see how the trend goes. Your initial expectation, if you hadn't thought about the intermolecular forces, would be that, well, for each of these groups, I'll see that boiling point increases with molar mass. But that's not what you would see for the last three groups, where you'd see that actually water, H2O, has a much higher boiling point than hydrogen sulfide, H2S, than hydrogen selenide, H2SE, than hydrogen telluride, H2TE. In the halogens, you'd see that hydrofluoric acid, HF, hydrogen fluoride has the highest boiling point. In group 15, you would see that ammonia, NH3, has the highest boiling point. Antimony trihydride comes close, but ammonia is still higher. What's going on here? Now, boiling point is not necessarily increasing with increasing molar mass, and the reason is that these molecules are special molecules, right? Ammonia, hydrogen fluoride, and water are hydrogen bonders. And so they have the strongest intermolecular forces out of any of these molecules that you're comparing them to. And what that means is they have physical properties that are influenced by those intermolecular forces, and it's going to take much more energy to boil a molecule that can hydrogen bond than a polar molecule that can't hydrogen bond, even if that polar molecule is much, much heavier has a higher molar mass than the molecule that can hydrogen bond. So I have an exercise to conclude today and to conclude the end of the week that I think will stand you in good stead for the quiz this week, where I ask you to take some data like this, make some predictions, and explain what's going on. The key thing I want you to take away is that stronger intermolecular forces are reflected in the physical properties of pure chemical compounds. Those physical properties would include their melting point, their boiling point, and even their surface tension and viscosity, which are some things that we'll get into in the next section of chapter 10. Molecular mass, molar mass plays its part. So the molar mass of molecules absolutely counts. What you should remember is that if there were no change in intermolecular forces, or molecules had similar intermolecular forces, the heavier molecule, the molecule with the higher molar mass, will have more notable physical properties, stronger physical properties. Its boiling point will be higher, its melting point will be higher, etc. But in general, intermolecular forces have a bigger impact. So if you have a series of molecules and you're asked to make a prediction or a comparison about their boiling points or melting points, the molecule with the stronger intermolecular forces is almost certainly going to have the highest melting or boiling point, except in really extreme cases of difference in molar mass. So intermolecular forces and molar mass are what determine melting point and boiling point in pure chemical compounds, but intermolecular forces count for more. Lastly, we're going to see that the strength of intermolecular forces is reflected in other physical properties too, not just boiling point and melting point, but also in properties like viscosity, resistance to flow, and surface tension, and the ability to exhibit capillary action and rise through a straw or a channel. So that's where we're going with our discussion of intermolecular forces. When we come back in the next section of the book, we're going to talk a little bit more about how intermolecular forces are related to these physical properties, particularly the properties of pure liquids. And after another example, that's where we'll pick up when we come back tomorrow. I'll see you then.